Chairman said that the system consists of primary F-type supergiant that's more luminous than Rigel, large enough to engulf half of Earth's orbit. So, Chairman?
Thank you very much. All right, let's talk about Epsilon Aurigae. I first heard about this star when I was a freshman in college about 20 years ago. My astronomy professor at the time was kind of a nut on variable stars. We got sun guys in the room, we got moon guys in the room. My astronomy professor was variable star nut guy. And we were studying stars whose brightness changes with time. That's what variable stars are. And he had an entire write-up on Epsilon Aurigae. And it was kind of interesting. And just kind of as a background, first of all, I'm Jeremy Veldman. I graduated from Christian Brothers University in electrical engineering in 1998. I actually took some courses in this very classroom, so it sort of conjures up some good memories and some nightmares. So, by the way, we're getting late here. So, what's that?
Did you have Bill?
I did not have I had doctoral lobby digital design in this classroom. And then Art Yanishka, probability and statistics. He kept me up at night, so fortunately those days are over. But anyway, I've had a fascination in astronomy for about 30 years now. And it's always been something that's intrigued me. I am one of the guys who watches the History Channel and the National Geographic Channel, so I do have that confession to make. Anyway, Epsilon Aurigae, we're going to talk about the star, we're going to talk about the system itself, the mystery of this star system, history, proposed models, and then the recent eclipse results, and then also sort of the current or conventional model for the star system. Most of the stars in our galaxy travel in multiple pairs, either binary or triple or multiple star systems. Our sun is a rare exception to that. And incidentally, there are actually some scientists who believe that our sun has a companion star. It's an unseen, either red dwarf or brown dwarf on the outskirts of our solar system, somewhere between 1 and 3 light years away, that we haven't found yet, that gravitationally interacts with the Oort cloud. And the reason they think that is because if you look back at the geological history of our Earth, you can see mass extinction events occurring in regular timescales. And there has to be a logical explanation for that. So it's interesting. Does our sun have a distant companion star that gravitationally interacts with the Oort cloud and pushes comet fragments toward the solar system that eventually collide with us? Personally, I don't think so, but the point is that the majority of the stars in our universe have companions that are bound to each other gravitationally. Epsilon Aurigae is one of those stars. Let's talk about the system itself. Just some background here. Some other names for it. Ans, Helatus, whatever. It's a magnitude 3 star when it's in its normal state, which means it's visible to the naked eye. And it's an eclipsing binary star, which basically means you have one object that passes in front of another object, similar to what we see here on Earth with lunar and solar eclipses. The primary star is an F0 supergiant star. And it was thought that it was somewhere between 15 and 30 solar masses. And it's 120,000 times more luminous than our sun, about twice as bright as Rigel. Put that in perspective, the star is 2,000 light years away. If it was placed as close to Earth as the star Sirius is in the constellation Canis Major, it would shine brighter than a first quarter moon from the Earth. As far as its size, if it were placed at the center of our solar system, Earth and its orbit would fit easily inside of this supergiant star. So that in and of itself makes this system incredibly fascinating. But even more fascinating is the secondary body, which has puzzled astronomers for nearly 2 centuries now. It's a dark body that has to be equal, pretty close in mass, to the primary, and it eclipses it every 27.1 years for a period of 2 years. Now, you know anything about eclipsing binary stars, most of them have periods a lot smaller than that, on the order of several days or months, at the most, maybe a year. But 27.1 years, and then the duration of the eclipse itself being 2 years, I mean, it's very, very strange. So let's talk about where it is. It's very easy to find. You know where Capella is. You can find Epsilon Aurigae. Capella is a very bright star in the constellation Aurigae. And just to the lower part of Capella, you can see there's basically an isosceles triangle of smaller magnitude 3 stars. The apex of that isosceles triangle is Epsilon Aurigae. The group of stars is also known as the Kids. There's another graph of it. You can see Orion. You can find Orion easily. If you go basically northeast of Orion, you can find Capella. And if you can find Capella, you can find Epsilon Aurigae. So all of you, your homework assignment tonight is to find the star Epsilon Aurigae. Of course, none of you will be able to complete it because we have a cloudy night. But next clear night, definitely take a look at it and see if you can convince yourself that this is the type of star that it is. So, let's talk about the history. It was first discovered by K. Fritsch back in 1821, and all he really noticed was that it was a variable star. Looked at it one night and noticed that it was faint, and basically just wrote, had anybody else notice that characteristic of it. 1847, 1848, Schmidt, Heiss, Erlanger, and several other people observed that it had a minimum and confirmed it as a variable star. And Schmidt actually observed it as a third minimum in 1874, 75. Really not much happened in the 19th century. It wasn't until Ludendorff in 1903 discovered that it was a binary star with a period of 27.1 years. And then in 1912, Henry Norris Russell published his first paper on the first analytical methods for binary star analysis. And 3 years later, Harlow Shapley applied these techniques and discovered that the system had a mysterious dark body or dark companion. There have been 7 eclipse campaigns in history on this particular star. The most recent one just ended, literally in the last couple of months. We'll talk about that. The first one that was measured goes back to the mid-1800s. So if you're feeling old, don't worry. Just measure your time on Earth in Epsilon Aurigae years. I'm 2 going on 3. So there's some 1,000 papers that have been published on this star alone. This star has made careers for a lot of professional astronomers. The mystery, like we said earlier, is that basically you have this incredibly massive supergiant star that is eclipsed by a dark body that we don't completely understand the characteristics of for as long as 2 years. And what's most interesting or most mysterious is that if this secondary body should have as much mass as the primary F star, then it should itself be luminous. But to this day, we have not seen any light come from the secondary eclipsing body. So why is that? And to put that in technical terms, the mass to light ratio of the eclipsing body is incredibly large, similar to the cosmological problem of dark matter, right? If you don't understand something, dark matter. That's kind of like the new thing now in astronomy. Dark matter and dark energy. So what type of object can eclipse a massive F-type star like this and essentially cause it to lose half of its brightness every 27.1 years for a period of 2 years? That's the mystery of the Epsilon Aurigae system. This is a light curve from the eclipse of 1955 to 1957. I'm showing you this just so you can kind of get a picture in your mind of what the eclipse actually looks like. You can see here, this again, just a sketch, starting up here around magnitude 3, and then during ingress falling to basically a magnitude of 3.7 to 3.8 as a minimum of for about 2 years. Slightly declines in nature, and then egress occurs at the end here. So this is the shape of the light curve for the Epsilon Aurigae eclipse from the 1955 to 1957 eclipse campaign. Getting back to Ludendorff, to try and explain the mystery of the star system, he proposed that there was a swarm of meteorites clumping together that could be blocking out the light from this system. Of course, the term meteorite being a misnomer here. A meteorite is an object that impacts the ground and leaves a crater. We heard a speech on that 2 months ago from the Cumberland Gap. A meteoroid is the actual rocky body itself, so the technical term should be a meteoroid swarm, but you get the idea. basically a clump of rocky bodies that's blocking off the light. And it wasn't a bad estimation for the time, but the problem is it's doubtful that a swarm of meteorites like this could be dense enough, first of all, to block off the light, and secondly, that it could stay together for that long a period of time without some type of body holding it together gravitationally. So the Ludendorff model was pretty much disproven pretty quickly, but he was on the right track. In the 1930s, three guys, Kuiper, Strongman, and Struve, who were very, very reputable astronomers for their day, came up with a very intriguing model at the time. What if instead of a clump of meteorites or meteoroids blocking off the supergiant star, we had an incredibly massive, supergiant star, several thousand times larger than our sun, that was large and cool, so it wouldn't be detected, that blocked off the light of the system. And that's what this diagram is showing here. So basically up here you have the F supergiant star, and then the dark eclipsing body being the supergiant star, supergiant star, about 2,800 times the sun's diameter. And this model right here received a lot of attention because these guys were very reputable in the 1930s. And at this point in time, Epsilon Aurigae was originally thought to be the largest star in the universe because of this star right here. But this model addresses the major concerns that the Ludendorff model had, being that this clump of meteoroids can essentially stay together gravitationally. So that problem was solved. But the Kuiper, Strongman, and Struve model still had a lot of weaknesses. First of all, there's no known supergiant star of this size. It's essentially, you compare it to Betelgeuse, one of the largest stars we know. Betelgeuse would be about a third of the diameter and 1/27th of the volume. And then also there have been no documented cases of stars this large. But the most significant thing is, quite frankly, it didn't fit the light curve. If you look at the light curve that we just saw from the 1955-57, it had a flat minimum. If it was a supergiant star that was blocking off the light of the F primary, then the light curve would look a lot different. So this received a lot of attention, but eventually it was thrown out. Koppel in 1954 was really the first one to present the idea of a disk of material in the system that blocked off part of the light. And he actually had a pretty good idea of the characteristics of this disk. It's essentially flat, it's semi-transparent, so some of the light can still shine through. Has a radius of about 6 astronomical units, declines slightly to the body's orbit. And he actually got into some of the actual characteristics of the dust ring itself. That's actually made out of particles, sand-like particles, and actually contains crystals of water and hydrocarbons. And he thought it had a mass of about 1 solar mass. So he was on the right track. 1961, HAC, the shell model. It's basically a central star encompassed by a large shell of material, dust material that has different layers of density. And this shell passes in front of the F supergiant star, blocking off the light. Not a bad idea either, but this was also disproven because it doesn't fit the light curve that we saw in 1955 and 1957. If this were the eclipsing body, you would not see a light curve that has a flat minimum. You would actually see a light curve that's more U-shaped or V-shaped because the object would block off the light of the entire star. And that's not what we see. So we have this problem of this very, very long eclipse duration with a flat minimum, and trying to find a model for the system that actually fits this. So in 1965, Shushu Wang came up with a model that is basically the conventional model that we use for the system today. And that is basically a dark cloud that passes in front of the star, that doesn't block it off completely, it blocks off part of the light. And then there's a central object inside of this dark cloud that gravitationally holds the cloud together. So you can think of a big cigar in space, somewhere between 5 and 10 astronomical units long and 1 astronomical unit thick, that's held together by a star, and the F star is never completely hidden from our view during the eclipse. So, and this actually fits the light curve of the 55 to 57 eclipse campaign pretty well. Much better than the shell model. But there are still some problems that need to be explained. Number one is, why does it stay as a dust cloud? I mean, gravitationally, shouldn't it flatten out into kind of a disk-like structure like we see in Saturn's rings? And also, why don't we see the central star? To this date, no visible evidence has been seen of any star in the dark body of this system. And also, because the F supergiant star was thought to be so massive, we thought that the central star had to also be massive. So if there's a massive star at the center of this dark cloud, we should either see the light from it, or it should be something that's very, very dark. And that's where you get into this black hole hypothesis. Cameron published this in 1971. And at that time, black holes were still fairly new, and again, they became kind of the answer to everything. You didn't understand how something behaved, black hole, black hole. But of course, this was disproven because when you look at the spectrum of this system, there was no X-rays were detected. X-rays are kind of the smoking gun of a black hole because you have matter falling into the ergosphere, and that shoots off incredibly energetic particles. So we don't see that. So the black hole hypothesis was discarded as being an explanation for the central object of this dark cloud. But Huang's model was a fairly accurate estimation for what we believe the Epsilon Aurigae system property and characteristics to be today. The last eclipse campaign, prior to the most recent one, was in 1982 to 84. This is a sketch of the light curve. Notice the difference in this curve from the one we just saw in 1955 and 1957. The biggest difference being this central brightening, which is one of the biggest mysteries of the star system. Not only that it flattens out, but mid-eclipse, there's a brightening in apparent magnitude of about 0.2. To this day, it's still a mystery. We're still trying to figure it out. But at the time when we saw these results, here's the actual data plot of the 1982-84 eclipse. We thought that it could be that the disk that's blocking the light off from the F-star component was actually slowly tilting to our line of sight over time and possibly revealing the light from the central star in the disk, which is what made the most recent, going into the most recent eclipse campaign, very, very interesting. We wanted to see if we could actually get more detailed data from this eclipse to prove that either there was a hole in the center where light shining through, or that the actual light from the central star itself was starting to reveal itself over time. So, 1980s, summing it up, Huang's model was basically correct. There was a slight mid-eclipse brightening of the 1982-84 campaign. Is this because the orientation of the cloud is changing over time, possibly revealing the central star? F-star is unstable. This F-star, what we're seeing is sepia-like pulsations, indicative of a star that's getting old and nearing the end. Talk more about that in a minute. The dust cloud itself in the eclipsing body cannot account for the majority of the mass of the secondary body. So we still have this problem. The majority of the mass has to be some type of central object, a star or something that's holding the majority, that holds the majority of the mass and keeps it gravitationally bound to the F-star. And we still don't see the light. There's no direct evidence of a central star because we still don't see the light from it. So that's basically where we were by the end of the 1980s and 1990s. Question?
If you're going to say this in a minute, I'll back off, but when you say there's no evidence for a central star, since we're looking at almost equatorially, there should be this Doppler effect as the F-star goes around the center, coming and going. Do you see that?
Doppler effect?
Right.
Yes.
Like a spectroscopic binary where you
Yes.
see the line shifting.
Yeah. We'll talk more about that when we get into the results of 2000, the most recent eclipse. But yes, you're absolutely right. You should see that effect. 85, the listener model. he actually built upon what Huang did. And what I'm showing here is basically, we were looking down at the system, top down in the system. F star over here, basically a cross section of the dust cloud. And in the center, instead of one massive star that should be visible, why not take that star and divide it into two stars that are ground to each other, ground tightly to each other, and essentially rotating each other? You can still have basically a massive central object, but it wouldn't be as luminous because instead of one bright star, you have two fairly massive stars that are less luminous. And that might actually solve the problem of having a massive central object instead of that's not visible. So the Lissier model, and this is actually another view, basically edge on, like you're looking at a coin. The dust cloud being right here. You can see some of the light shining through top and bottom from the central object, and then the F supergiant right here. So, and here's actually another one. Eagleton, Pringle, and Schmidtke also had a very similar model, Lissier, which is basically, again, the same thing. F primary supergiant star, and then the dust cloud with two stars in the middle that are gravitationally bound to each other, orbiting each other, kind of like a gravitational egg beater, carving out a hole in the center of the dust cloud. And that seemed to fit the characteristics of the light curve pretty well. So going into the recent eclipse, this was kind of the understanding of the Epsilon Aurigae system. So we talked about this. Mid-eclipse brightening was discussed at the Tucson meeting in 1985. So we didn't really see mid-eclipse brightening in the 28 or 57 eclipses. And again, the idea was gradual precession in the disk orientation. So over time, is the disk tilting slightly to our line of sight where we're actually seeing the central object. So that really set the stage for the most recent eclipse. So 2009 to 2011, the eclipse began right around August of 2009. All of 2010, the star was essentially dark. And most recently, March, April, May 2011 was egress, where the eclipse was ending. So these four guys right here were central to organizing the most recent eclipse campaign and gathering data and helping us solve essentially the mystery of the Epsilon Aurigae system. The main guy being Jeff Hopkins. This guy's been around a long time. He observed the 82-84 eclipse campaign, built a website, ton of information about Epsilon Aurigae. And Leadbeater's another guy. Brian Kloppenberg, 27-year-old graduate student at the University of Denver, did quite a bit of research on actually not only observing the star, but taking pictures of it while it was in eclipse. So, and what makes the most recent eclipse campaign different from the previous one is the advances technologically. When you think about 27 years, 1984, where we were compared to where we are today. The development of computers and computer-aided positioning control with lasers and interferometry, I can't even say the word, it's getting late. Interferometry, which is basically combining multiple telescopes to get a higher resolution image. So if you had a 1 meter telescope, you're basically seeing limited to 1 arc second of resolution in space. You take two 1 meter telescopes separated 100 meters apart, and now you've just increased your resolution by 0.001 arc seconds. So as technology advances, we can start seeing more and more characteristics of these stars and these systems. And you can use a technique called phase closure, which is basically where you're taking several images of a system and using computer modeling to generate a physical projection of what the system would look like. Here's a picture of what we see, of the actual eclipse occurring based on this interferometry technique. And this was This was filmed by, or this picture was taken by Kloppenberg. So you can see the F-star here, and you can see the disk, the dust cloud, the dusty disk passing in front of the star, blocking off the light. And this is an array, the Char array that was used to take some of these images from the eclipse. Again, you've got telescope here, and very, very powerful array. To give you an idea, if there was a Walmart on the surface of Mars, this array of telescopes could count the individual parking spaces. Pretty impressive. Light curve from the 2009 to 2011 campaign. Data points from observatories all around the world. You can see a very, very similar characteristics to what we saw in the 82 to 84 campaign. Again, you have this mid-eclipse brightening here. Talk more about that in a second. One thing that,
excuse me, I presume that gap was when it was in the daylight.
Exactly. Yeah, you have a gap here in mid-eclipse. You had the same thing in 84. You're getting into the summer months when the sun is blocking out the Aurigae system. One interesting result from the most recent eclipse campaign is essentially, when you're looking at the spectra of the system, you can see the three main components: the F star, a B star, and then the disk here. The presence of ultraviolet light in the system's spectra is essentially the signature of the presence of a B5V main sequence star in the center of the disk. So this is the most interesting thing here. Now we have an understanding of what is going on in the center of this disk. And then of course the F-star component. And it's believed that the B star in the center of the disk is about 5.9 solar masses and about 4 solar radii. And then, of course, the infrared spectra gives us an idea of the properties of the dusty disk. Another interesting result from the 2009 to 2011 eclipse campaign is this stepwise function that Robin Ledbetter and Stencil actually published in their mid-eclipse paper. And what this is indicative of is a disk showing ring or possibly arc or spiral-like structures, similar to what we see in the rings of Saturn, kind of a Cassini division. And it's kind of interesting because that tells us some more properties of the actual disk itself. And does matter tend to distribute itself in general in the universe in kind of a density wave-like pattern, like we see in spiral galaxies and then also in other planetary nebula. So these results are giving us some more information about the composition of the disk itself. So the results, originally going into the most recent campaign, we thought that the mass of the F star was somewhere around 20 to 30 solar masses. It turns out that does not fit what we're seeing in the light curve. And they rethought the whole model. Not only the central object of the disk, but also the F star itself. So now it's believed that the F0 supergiant, instead of being a really, really massive star, is actually a much less massive star, somewhere around 2 to 3 solar masses. And it's actually about 2/3 of the mass of the disk itself and its contents. So the F star is actually a post-AGB star, which means it's dying, it's moved off of main sequence, and eventually it's going to fade away. The disk has about 1 Earth masses, composed mainly of large dust grains, similar to like sandy particles. Didn't see any evidence of ices or molecules in the disk. And it appears to contain some type of extended atmosphere, and has tidally induced density wave structures like rings or arcs. We just talked about that. We still don't know a lot about the nature of the disk. The main mystery being, why do we find the disk around the older B-type star instead of the younger star? Don't completely understand that. Here's a schematic diagram of the Epsilon Aurigae system. I'll just walk you through it. You got the F star here, 135 times the width of the sun, 2 to 3 solar masses. And then you have the basically the dust cloud over here. The distance between the two is about the same as the distance between the sun and the planet Neptune. Central object is a B-type star, about 5 to 6 solar masses, and 3 times the width of our sun. And the mass of the disk itself is about the same as the mass of the Earth. And it's about 7.6 astronomical units wide, and it's about 0.5 astronomical units thick. So this is the schematic diagram of our most recent interpretation of the Epsilon Aurigae system, based on the most recent eclipse. So conclusions, the F star is not nearly as massive as we thought. It's not a 30 solar mass star, it's about a 2 to 3 solar mass star. It's dying. It's not going to go nova. It's not going to have a spectacular end. It's not going to go out with a bang. It's just going to eventually fade away. In the center, you have a B5 main sequence star that is more massive than the F-type star. It's not 2 stars, it's 1 star. The mid-eclipse brightening is still not completely understood. It could be due to a combination of factors. It was originally thought possibly gravitational lensing was the result of this, but there's not enough mass in the system for that, so that's out. It could be the F star propagating through the central hole, kind of like a donut hole in the disk. The more likely explanation is what we see during the out of eclipse variations. See, even though the eclipse of 2009 to 2011 is over, we're still observing the system. Astronomers are still observing the system because of the F star itself. It undergoes Cepheid-like pulsations. And we do see a mid-eclipse brightening of about 0.2 magnitude, or I'm sorry, 0.1 in magnitude. So it could be a combination of that, and then also what's called air mass correction, which means when you observe the eclipse at certain times during the year, there's thicker layers of the atmosphere that are distorting your effects that need to be corrected. And then, again, the disk's exact properties are still being studied. They're still somewhat of a mystery. A lot of neat pictures on the internet of the Epsilon Aurigae system. I've given you guys a lot of words. So you can see here an artist's depiction of the F star here being blocked off by this large dusty disk. And then the B star light shining through. Try to wrap your mind around the width of this disk being somewhere between 7 and 8 times the distance from the Earth to the sun. So it would take light somewhere between 8 times 7 to travel from here to here, 56 minutes. And here's another great picture of it. You can see the F supergiant here, and you can see the dust cloud here with the blue star. So 3 components: F supergiant, 2 to 3 solar masses, dusty disk, 1 Earth mass, 7 to 8 astronomical units wide, and then you got the central B-type star between 5 and 6 solar masses. And that's essentially our understanding of the Epsilon Aurigae system today. That's my talk. Any questions?
I've got a major problem with the F star already having left the main sequence, yet a B star is still in existence. It should have become a red supergiant and exploded long before, unless it was just newly formed with a collision or merger of some other stars.
Right.
Is that ever brought up? Like, why is there even an O star in existence with the F one already leaving the main sequence? That should have peeled off first.
Right. Yeah, the B star is the main sequence star. You think that one's more massive than the F star. The only explanation, or the potential explanation, is that the F star at one time was much more massive than the B star. And then over time, some of that mass has been stripped off.
Or, like the blue stragglers and globular clusters, where you have these old clusters with blue stars in them just from mergers of others. This isn't in a globular cluster, so chances of a merger would be a lot less, but I can't think of any way to explain that.
Yeah, why is the F star
Yeah.
essentially a dying star? It's off of main sequence. and the blue star
It's
is still on the main sequence.
Yeah.
That is interesting. I have not read anything in the literature that explains why that is, as well as why is the disk of material around the F-type star instead of around the B-type star? Is it because the disk of material always coalesces around a more massive object? Or did the disk form there as a result of the F-star expanding and then the outer layers of the star itself becoming loosely bound gravitationally to the star, and then the gravity of the blue star stripping the material off? Don't know. There's still a lot of mysteries. There's still a lot more questions than answers for this particular star. It's like, we think we have it solved, but we're not going to get another crack at this until 2036.
Yeah.
And unfortunately, most of us aren't going to be here.
Yeah.
Question?
Does anything interesting happen to the light curve 13 years after minimum and 4 years before and 4 years after minimum?
13 years after minimum?
Yeah, that would be when it's on, the object's on the opposite side.
Oh, okay. The only thing that's been observed is, again, there is a variation in magnitude between 0.1 and 0.2, out of eclipse variation. The star itself is kind of tricky because it is a pulsating star, but the period is not a regular period. So we still don't completely understand the characteristics to the point where we can model it accurately. So I don't know if that answers your questions or not, but yeah.
That would be an interesting moment to look. Also 4 years before and after, because if I'm doing the math right, that's when the Lagrangian points would pass in front of that star. And there might be some mass out there leading and trailing the disk.
There could be, yeah, there could be. Observations are still going on right now. Even though the visual eclipse is over, there is still spectroscopic data being taken in other parts of the spectrum. So observations are continuing right through the month of November. Yeah,
Like an asteroid belt
Yeah,
situation.
something like Trojans or something out there.
Well, you also mentioned the sort of Cassini-like division in there, and if it works the same way as the gaps in Saturn's rings, then there are bodies in there keeping those gaps open. Shepherd things, those shepherd moons, or in this case, sort of smallish planets or moonlets.
Absolutely. Yeah, absolutely. I've not seen any direct evidence of that yet, but that's been proposed. There's actually an article in Sky and Telescope magazine that Jeff Hawkins wrote back in, it was 2009, that discussed some of that information.
Things like a final exam in astrophysics.
So, this is the tip of the iceberg, by the way. There's a lot of information out there. A lot of information just on this one star. We talk about one star. So,
Part of what you was talking about sounded like, reminded me of maybe the Ring Nebula being part of the binary.
Yeah. Almost patterns and stuff.
Yeah.
but is there any other system out there that you guys know of that's this big?
No.
That's this massive?
No,
I mean, Zeta Aurigae is another interesting star, but its period is much lower than Epsilon Aurigae. I mean, a dust cloud 7 to 8 astronomical units wide, that eclipses the light from a star that's 160,000, 120,000 times brighter than our sun. It's just unusual.
Well, is that number still good after the scale back to the?
Yeah,
Seems like it'd be less now.
they're saying that even though the mass is lower, because of the size of the star and the surface area, you can still have a really, really bright supergiant star.
Gosh, if it's Cepheid light, you could pick out the actual luminosity off the period luminosity curve or Cepheid variable. So like that would be a way to tie that down.
Absolutely.
But is it a Cepheid or just sort of a?
It's Cepheid light.
light.
It's not Cepheid, it's Cepheid
I
light.
know, okay.
So, all right, guys. It's 10 o'clock.
I'm almost about to forget, nominate committee and all that. 2 observance sessions we have this month. second one is November 26th at the same time down at Barton Sugar Farm. So that's our two, they're in the newsletter, so that's our two observers.
What time?
Same time, yes.
So,
Fifth grade, same time. I didn't put it in there about, I assume.
because daylight saving time goes off this
Yeah,
Sunday.
tomorrow night, we can change all the clocks, all that.
And on the 8th, we've got a near-Earth object,
Enjoy.
fairly bright.
Think he's home on time?
Absorb it.
I think you did all right. Thanks a lot for coming.
So I haven't looked at what the geography is gonna be of that, what